Grimsby Secondary. Ada will be giving us a guided tour into the rich and fascinating world of imaginary numbers. I hope we don't lose an eye here. And guess what? They aren't just a fiction of the mind. Whenever you're ready, Ada, please take it away and wrap us up for the night.
Yeah, so thanks for that introduction. So for my presentation, I hope to give you a kind of guided tour of the world of imaginary numbers. And I do have a few questions that I'll be asking you. So if you have a paper and pencil handy, then that would be great. And hopefully you still have the brain power left after all those great presentations. So I'd like to get started by asking a fairly strange question, and that is, which of the following of these really exist? You can type in the chat what you think, maybe give an argument for your answers. And there definitely isn't a right or wrong answer, but I think it's an interesting question to consider. Okay, we have some different answers that are coming in. So are you guys saying that like only the number 1 exists out of all of these? Okay, that's very interesting. So I know personally when I first saw this question, I said like all of them exist except for infinity, because I know that infinity can kind of take on many different forms. And we sort of saw that earlier as well. But the main takeaway that I want you to get from this question is that all of math lives in its own kind of abstract world. So you could say that none of it really exists. But maybe the question of existence doesn't really matter. But what matters more is if a mathematical idea is a useful tool to solve problems. Like, for example, you might consider infinity to not really exist, but we know that the idea of infinity is an extremely useful one, both within math and for solving problems in the physical world. And if you aren't sure that infinity is a useful idea, then I'll just tell you that that's what calculus is all about. So you can keep this idea kind of in the back of your mind, just for the rest of the presentation. So now we can get into imaginary numbers. So the reason that imaginary numbers are a thing is because of what happens when you try to solve an equation, like x squared plus 1 equals 0. So what is it that happens when you try to find a solution to this equation? Yeah, so you get like an error, or you can't take the square root of a negative. Yeah, that's right. So like you'd have to take the square root of a negative number in order to solve this equation. But you might know that that's something that we're not allowed to do. And for a long time, mathematicians said that all of these equations involving the square root of a negative number have no solution. But mathematicians want to be able to solve all equations. So they were forced to accept the fact that the real numbers would not be sufficient. They were going to have to extend the number system into like imaginary numbers. So what they did is they defined I to be the square root of -1. And this probably seems like a pretty daunting thing to do, because it still kind of feels like, well, what actually is I? And that's definitely like a reasonable question to ask. But if you just put aside those feelings and kind of explore what happens when you combine this definition with the rules of algebra that we already know, then you can gain some understanding that might help to address your concerns. And there really is a larger lesson here about math in general. Math is really about trying stuff and seeing what works. There's never been any harm in like just trying to see what would happen. Although I wouldn't take that attitude into your chemistry class. So even if what we're doing feels shaky, sometimes you just have to pretend to accept a definition and see what things would be like if it were true. And if you feel like you've gotten somewhere valuable with it, then you can always go back and refine the foundations. And if it feels like maybe you've created some paradoxical nonsense, then you've still gained an understanding on why that definition maybe wasn't such a great idea. So now with our new definition, that I is equal to the square root of -1, I want you to try solving the equation 8x squared plus 16 equals 0 in terms of I. So I'll give you a minute to try that, and you can put your answers in the chat once you have one. I tried, James. I thought the hints would be at least a little bit helpful. Yeah, we've got some good answers coming in. So I think I'll go over what the solution would be now. So to solve this problem, you would start by subtracting the 16 and then dividing by 8. So then you'd get that x squared is equal to -2. And so then x is equal to the plus or minus square root of -2. And that's where the two solutions come in, because you need to take the plus or minus square root. But then because we want an answer in terms of I, we can use the property of radicals, that was the hint on the previous slide, to write this as the square root of -1 times the square root of 2, which then is I times the square root of 2. So then the two solutions are plus or minus I times the square root of 2. Also, you can always verify either of these solutions to make sure that they make sense. So I plugged in the negative solution back into the equation, and it worked out to 0 like we expected. So the solutions to the previous equation were examples of purely imaginary numbers, but there is a broader class of numbers that involve the square roots of negatives, and they're called complex numbers. And they're just numbers that have a real part to them as well as an imaginary part. So an example of a complex number would be something like 5 plus 2i or 3/4 plus I. And you could say that all imaginary numbers are just complex numbers that have a real part of 0. So I think it's fun to look at now this fuller picture of our number system. Now it's complete with complex and imaginary numbers. And based on this diagram, you could also say that actually all real numbers are complex numbers. They just happen to have an imaginary part of 0. So how did imaginary numbers get their mysterious name? Well, mathematicians were initially skeptical at the idea of them. They couldn't think of any practical explanation of what the square root of a negative really meant, so they called it an imaginary number. An example of this is the story of an Italian mathematician studying the cubic formula. He observed how an expression with imaginary numbers must be equal to a real valued solution to a cubic equation. And this did not strike him as evidence that imaginary numbers could be a powerful tool. Instead, he claimed that the result was subtle and useless. But the absurd story with imaginary numbers is that their name has stuck, even when they're now an accepted and useful part of mathematics and science. And another name that's been suggested for them is lateral numbers, and you'll have a better understanding of that a little bit later. So you might also be wondering at this point if it's reasonable to just fundamentally change math by extending the number system like this. But actually, the need for imaginary numbers falls into a pretty natural pattern based on the history of numbers and solving equations. Like there was a time when the equation x plus 3 equals 1 didn't have a solution. It was only when someone thought to use negative numbers that it could be solved. And like similar lines of thought followed for rational numbers. and also like irrational numbers for solving something like x squared equals 2. And throughout history, there was a great deal of controversy surrounding each of these leaps, just the same as with imaginary numbers. But really, they turn out to be a completely natural extension of our number system, and they don't create any major contradictions with the rules of arithmetic and algebra, which is important if they're going to fit in with the rest of the numbers. So now the next natural question might be, like, does this pattern continue on? Do we need more complex numbers? Like, are there still more types of equations that we can't solve in our complex number system? But actually, as part of something called the fundamental theorem of algebra, it's been proven that we don't need anything beyond the complex number system. And the proof shows that the set of complex numbers is algebraically closed, which means that equations involving basic operations can always be solved with another complex number. That sounds like pretty great news to me. I don't know about you. So now we're going to look at a really cool and fundamental property of I, and that is the pattern in its successive powers. So we know that I to the first power is the square root of -1, and so then I squared is equal to -1. So see if you can fill in the rest of the powers here. And just know that your answer should be in terms of I, meaning that you shouldn't see any square roots of negative numbers. So you can type in the chat just when you're done. Yeah, but what about I cubed? Does anyone have an answer for that one? Negative I. Yeah, that's good. Okay, I think I'll go through the solution now. So for I cubed, you could think about that as being I squared times I, which then is the same as -1 times I. So that's negative I. Then for I to the fourth, you could multiply I cubed by I. You can see that ends up being 1. And so you could keep like multiplying each answer that you get by I to kind of fill in the rest of the chart here. So now, is there any patterns that you notice here in these powers of I? Yeah, it has some kind of repeating pattern going on. Yeah, so like the pattern that I want to highlight here is how the powers of I repeat in a cycle of 4, which I think that's pretty neat. And it also leads us to a place where we can start visualizing complex numbers on the complex plane. So we can visualize the pattern that we just observed by interpreting multiplication by I as a 90-degree rotation on the number line. But just before you try to make sense of that, first picture just a regular number line. You could imagine that multiplied by -1 has the effect of rotating things by 180 degrees. And so multiplying by I is like doing a 90-degree rotation, because we know that if we rotate by 90 degrees twice, then that's the same as like a full 180-degree rotation, which then matches up with the fact that I squared is -1. So because of this, we can create a complex plane where the imaginary axis is perpendicular to the real number line. And the complex plane is a great place to visualize the algebra that we can do with complex numbers. And this rotation idea also starts to explain how complex numbers can be helpful to model things with a periodic nature to them. So think about waves, which could represent light, sound, or maybe a vibrating spring. And complex numbers are even used by electrical engineers because of the periodic nature of alternating current. And doing calculations with complex numbers turns out to be easier and more efficient than with real numbers. And you might be thinking that we already have like our trig functions to model periodic motion, but the unique way that the algebra of I behaves can make calculations with these types of models much easier. And this is also where the name lateral numbers comes in, with the idea that imaginary numbers are perpendicular to the real number line. So now we can start using the complex plane to visualize complex numbers. If you're given a complex number in the form that we saw earlier, you can pretty simply just graph it as a line segment with the corresponding real and imaginary components. But another way of looking at a complex number is instead it being defined by a magnitude and an angle. So you can try to picture that if you're given like a certain angle and a certain magnitude, which is just like the length of the line, that defines a unique complex number in the plane. And with a bit of trigonometry, you can convert between the different forms. And also, if you know a bit about vectors, you can probably see how complex numbers are actually very similar to them. And one of the interesting things about these two interpretations of a complex number is how some complex number operations are better suited to a particular form. So for example, adding complex numbers is fairly straightforward when they're in component form. You just kind of add the corresponding components. But in polar form, adding complex numbers just doesn't make as much conceptual sense. And with multiplication, you can do like the algebra that results when the numbers are in rectangular form, just amounts to like expanding out the brackets. But if instead you try multiplication with the numbers in polar form, you gain a significantly different insight into what's going on. I won't go into the details, but I leave it to you to figure out what multiplication looks like in the different forms, and also what it looks like visually on the complex plane. Okay, now we'll look at a real-world application of complex numbers. And it's not as if we need a justification to do math, but I think it just sounds cool to say that you know a real application of imaginary numbers. So imaginary numbers are part of the Schrödinger wave equation. And this equation is really what's at the heart of quantum mechanics. And it describes how particles behave at the smallest scale. So you could say that complex numbers play a role in our best theory for describing the most fundamental aspects of the universe. Pretty cool. So I certainly don't understand like very much about quantum mechanics, but it's definitely like fun to see what the future holds for further learning. And the last thing that I want to leave you with is a little sneak peek of Euler's identity. So it gives us a third way to express complex numbers, this time in exponential form. And so a complex number with magnitude 1 in a particular angle can also be written as e to the I times that angle. And e is a constant around 2.7, and it has to do with continuously compounded interest. So this notation of writing complex numbers in exponential form is what gets used all the time in physics. This is because multiplying exponential functions together is easy, because you can just add their exponents, which corresponds to adding the angles of complex numbers. And this is a lot easier than trying to multiply like sums of sine and cosine waves together. And one of the ways that you can show this identity is by looking at the series expansion of e to the x, cosine of x, and sine of x. It can be shown that each of these functions is actually equal to the infinite sum of terms that follow the pattern that you can see there. So just taking that to be true, the last problem that I have for you is to show that e to the I times x is equal to cosine of x plus I times sine of x. But just before you like work on that, I'll just finish off my presentation. And I mean, you can come back to that question if there's time. And also, if you've seen what some say to be the most beautiful equation in math, then this is actually like where it comes from. By plugging in like an angle of pi radians, you get that e to the I pi is equal to -1. So that's pretty cool. So thanks for coming to my presentation. I hope that your mind feels a bit more enriched with your new knowledge of complex numbers, and also have a really good YouTube playlist if you want to check that out. Okay, that's it.
Thanks so much, Ada. That was absolutely awesome. I love the way that you developed the real and complex plane. And I also thought that it was kind of neat how we almost came full circle, because Shahad started talking about a letter that was written to Euler, who was like the best mathematician at that time. And now you're actually closing by talking about Euler's identity. So it kind of came
that's
full
true.
circle from where we started. So thank you very much. Yeah, thoroughly enjoyed it.